Okay, I think that we can start. And good afternoon, everybody. Welcome to the AutoChem Webinar Seminar 2021. And my name is Andrea Trabattoni from Daisy. I will chair this webinar, and it's a pleasure for me to introduce Carla Figueira de Morisson Faria. And she's a professor of physics at UCL in London. And she's a great expert of theoretical strong field laser matter interactions. And today she will speak to us about the dissecting intra-cycle quantum interference in ultrafast photoelectron holography. And before giving the stage to Carla, I remind you that you have on the portal the live Q&A session in which you can write questions, and at the end of the seminar we will go through the questions. We will ask the question to Carla, and we have the possibility of triggering some nice discussion. And with this, I really would like to give the stage to Carla, please.
So Andrea and all the AutoChem participants, thank you so much for the invitation and for the nice introduction. In my talk, I will address ultrafast photoelectron holography and how one can explore this, especially from a theoretical point of view. So let me make a share. It's sharing. Brilliant. Okay, all fine. So my talk will be about dissecting quantum interference in ultrafast photoelectron holography. I'm going to focus especially on intra-cycle interference. And it's a pleasure to be here. This work has been done in collaboration with several groups, but the core of it with my group at UCL. And I'll start with a brief introduction and a motivation. So why do we care about photoelectron holography and how this could in principle be used to image matter in the sub-femtosecond time scale? I'll also consider key questions. I'll discuss some of the existing approaches, and then I'll talk about the approach that we have been using, which is the Coulomb quantum orbit strong field approximation. And I will then go through really this dissecting business. So look at well-known and overlooked holographic patterns, look at excited states and what happens if you have polarization of targets, and applications, especially with regard to looking at parity of orbitals. And then I'll talk about multipath interference, and I'll state my conclusions. So to start with, many of you are familiar with strong fields and photoelectron holography, but the key idea that we have in ultrafast photoelectron holography is that we can retrieve the structural and dynamical information from a target using photoelectrons. And the idea of it is more or less like what you have in conventional holography, where you have a probe signal, you have a reference signal, and you're going to use the phase differences between these signals to try to get a 3D image of the target. So typically, in the seminal papers in which people were looking at photoelectron holography, they started to look at different combinations of trajectories, because in our field, we can always describe laser matter interaction, or most cases, at least in the parameter range we are using, as a combination of electron trajectories in different quantum pathways that reach the detector. So what happens if you have some electron trajectories which are leaving and going directly to the detector, but you have something that is backscattered? What happens if you have something that is forward scattered, and what happens if you have something that is behaving in a different way? So typically, you traditionally use something that is probing this target, and a reference signal. And these pictures here you see, they are from the seminal papers. And you can see that you have several patterns that then you can use, hopefully, to retrieve this target. And there have been several studies. For instance, this is an example of a typical photoelectron holography, the spider. So here you can see you have this structure here along the polarization axis. This has been measured in the early 2010s, first measured, but meanwhile, many people have measured it. And you have this when you look at this plot of photoelectron momentum distributions coming from an intense laser field, you see that you have these fringes, and this is well known as a spider. Another example, which some people may say, maybe not, this is a resonance. Well, we disagree, and I'm going to come to this point, is a fan-shaped structure which was identified in the late 2000s near the threshold for several noble gases. Here there are some examples. And key questions for us were, okay, you have these holography patterns, you have some information that they are due to several laser-induced pathways the electron can leave and reach the detector during strong field ionization. And these pathways, they interfere, are going to have phase differences, but we wanted to know a few things. We wanted to know how these patterns form, what is the influence of the Coulomb tail, because you not only have a very strong field, but in principle, you also have a long-range potential. You would like to know also what is the role of ray scattering, because we always talk, okay, we have a ray scattering pathway, maybe a direct pathway, but what is really going on? And our conclusion when we're studying these is that the traditional oil-based approaches were not doing the job, because what people were using to study holography and to describe holography were some simple main model, in the sense that you have something that is mainly classical, but then you include some phase shifts by hand. And in this case, you would have, if you have a direct electron, no rescattering, rescattered electrons, you have soft or harsh scattering. Or you can use the strong field approximation, which already comes with phases, but approximates the continuum by a field dressed, plane waves, by Volkov waves, so that, again, you don't know what is happening to the tail, and you are going to have a very clear-cut distinction as a direct, the electrons, so electrons reach the detector, arrive at the detector, and rescattered electrons, where you have these collisions, and you could say, okay, this is soft, this is hard, based on the angle of rescattering. Now, what happens is that if you include the residual Coulomb potential in the continuum propagation, these concepts of direct and rescattered are going to become blurred, because maybe your potential is going to deflect your electrons, but is not going to make it undergo a hard scattering. Maybe you're going to have something soft. So where do you draw the line? And the dynamics is going to change a lot. This is something that has been studied for quite a while. And you see that it is really not the same. And for that purpose, many groups have started to look at how to go beyond the strong field approximation. And many times this includes going through path integrals, which was our case. But you see, you have families of orbit-based methods doing that. In many cases, it was, okay, let's go and consider you have this plane wave continuum, but we're going to construct some Born type series and include rescattering or change the asymptotic wave onto which you project, the asymptotic state onto which you project, or introduce some distortion. or for instance, this work using the Econal approximation, Econal-Volkov approximation. So there is a whole family, and this is a family tree, in fact, that we organized from our review on photoelectron holography, which was published recently. And I'm going to focus here on one, which was the one we developed, which is the Coulomb quantum orbit strong field approximation. The advantage of this method is that you have tunneling, you have quantum interference, it's orbit-based, and it allows you also to dissect different types of interference because you can switch things on and off. And this is an example of what we can get. We have a spider, we have a fan, we have several structures, and you can see that they are reproduced also by the strong field approximation, by the time-dependent Schrodinger equation. And an advantage as well is that you can treat the potential and the field on equal basis. You don't have to make any kind of assumption and put the potential perturbatively. So just to give you an example, what we do is we start from a transition amplitude, from the ground state or a bound state to the continuum. You can write this in terms of an integral equation. Now we project onto a final state. So this is ATI, basically. So we are going to have a bound state, and you want to take this electron, which is in the bound state, to a continuum state. Here, I haven't made any approximation. We're going to consider still the full time evolution operator associated with the full Hamiltonian, which contains the potential and the field. And we consider the interaction in the length gauge. So instead of constructing a field-dressed Born series, what we do is we use path integral methods. And with these path integral methods, we are able to describe this as a multiple integral, which can also be where you have an action, time-dependent action contains everything. You have a prefactor, and this embeds the potential, embeds the field, and we can solve them using saddle point methods. And in this case, you're going to have an intermediate electron momentum, intermediate electron coordinate, and you're going to have also some energy conservation at tunneling. So it's pretty much like what you would do under normal circumstances, but you have more variables to take into consideration. And you are going to end up with a transition amplitude that is summed over many orbits. So orbit-based method. And here we have the prefactor. So if you look, you can see that you have here a stability factor, which is associated with the orbit. Here you have this prefactor also contains information about the initial bound state, and you have an action which is propagating from this initial bound state to the continuum. So far everything is good. And a good point about this method is that you can use only four contributing trajectories per momentum, which you can switch on and off at will. Because effectively, what we did is we solved this as a boundary problem instead of starting with many trajectories and launching them and forward propagating. So this is cleaner than other types of Coulomb distorted methods. But the price that we had to pay was that this was less flexible, exactly because we were solving a boundary problem instead of launching 10 to the 8, 10 to the 9 trajectories. But this, you have a price. So pretty much we could identify 4 relevant types of orbits. They were first found by Jan, Propojenko, Vrakin, and Bauer many years ago, but we agree with them. The first one is very simple. It just is an orbit that leaves from the same side of as the detector and reaches the detector directly. The other two which we call orbit 2 and 3. They are like laser dress hyperbole. So basically what is happening is like as if you're launching a satellite, they're leaving from the opposite side, but they are under the influence of the field. So they go from the wrong side and then they reach the detector. This orbit 3 doesn't really exist in methods such as the strong field approximation. In fact, this would be degenerate in the strong field approximation. And what happens is that interacts more with the core than orbit 2 because the transverse momentum changes its sign during the propagation. And orbit 4 is something that goes around the core. So this is pretty much like what you would have in a scattered orbit. And if you have a look at the overall distribution, you can see if you add 1 cycle, 2 cycles, or 4 cycles, you see very clearly the ATI rings here. You have all these holographic patterns. And if you compare with the TDSE, which we compared with using QProp, you can also see that you have a good agreement and you have the main structures. Here is due to orbit 4, which we managed to get later on. Here in these plots, we used orbit 1, 2, and 3, and we included events, ionization events over 1 cycle, 2 cycles, and 4 cycles. You see, it gets more and more symmetric as it should be. And everything is there. ATI rings, fans, spider, and side lobes. Side lobes are these elongated features that you can see, and we're going to analyze all of them, all of these structures and a few more. And we see, if we look at what are the contributions of single orbits like orbit 1, 2, and 3, if you have no prefactor, basically what you have is orbit 1 and 2, they are going to be very much localized along the polarization axis. Orbit 3, not so much, occupies a region, and here you have acoustic. If you include the prefactor, you see that this orbit is much less stable, which is something you expect because it's something in between direct and rescattered. And this here is deflected more than this one. And one thing that is interesting is that people always say the side lobes come from interference effects, but can you see here that you have already these lobes? And you're going to have maxima that are not at the origin. So what is happening is that there is something already mapping the final end initial momentum. Remember that this plot here is not done with regard to the momentum with which the electron leaves, but with regard to the momentum in which it arrives at the detector. And you're going to have Coulomb forces and you're going to have acceleration and all things going on. So this is nice because side lobes, normally people attribute them to quantum interference, but you don't need quantum interference to find the side lobes. If you look, this is just one type of event and they're already there. So what is going on? What is going on is that if you plot the imaginary part of the action which is associated with the ionization probability, you are going to see that as a function of the momentum component perpendicular or parallel to the laser field polarization, in the strong field approximation, it is most likely that the electron ionize at 0 momentum, because that's when it's this is narrowest. That's when the barrier is narrowest, and it's much more likely that it's going to leave. So this imaginary part of the action has a minimum. But for the other cases, what you see is maybe you could have a minimum, but you still have a little bump for orbit 1, because orbit 1 is just being pulled back. But for orbit 2 and 3, the story is different. And in pretty much all cases, you see that if you plot this as a function of the final momentum, you are going to have 2 minima. not one. Because you need to imagine that you have a central force pulling this electron apart from the field, which is something that we always take into consideration. And this central force is actually changing the dynamics and is making the electron sometimes leave with non-vanishing momentum, or it's also changing this ratio between the intermediate momentum, the initial and the final. Now, if you look at holographic structures, and this is something contentious, I know, because some people looked at the thing for many years, and there were different explanations. For instance, some people say, this is a resonance. Why is it a resonance? Because you can relate this to a single Legendre polynomial, and you find this in the multiphoton regime, and you're going to have this kind of fringes. Or you could have laser dress hyperbole that have neighboring orbital angular momentum. Now, is this a resonance or is not a resonance? Because if it was a resonance, when you go to tunneling regime, you wouldn't expect to have the fan, but you still have the fan. And the models based on resonances then start to disagree. Also, this was what the Kansas group said, because they said, okay, you have an intermediate state with well-defined angular momentum, but this doesn't always hold. And the Rostock group, they looked at the quantum interference of several types of trajectories and say, okay, this is what is happening with the fan. But nobody from these people have done direct computation to see how it forms, because exactly of this, because it's very difficult to switch on and off types of trajectories and keep the phases. So we decided to have a look. And what you see is this is what you get with the QCSFA, again, over 4 cycles. This is what you would get with the standard strong field approximation. And this is giving you some information about what you have with the time-dependent Schrödinger equation. You have the same number of maxima and minima in the fan. You have some discrepancies in the polarization axis, but this is due to Arbitrary. We fix it later on. And if you look just at intra-cycle interference between orbits 1 and 2, you see that the ionization events are displaced by at most half a cycle here. And you have here this divergent structure, which is clearly match fan. This is only orbit 1 and 2, one of those hyperbole and the direct orbit, but in the presence of the Coulomb potential. And you do get the fan. And what you see, in fact, is that this Coulomb potential is distorting these orbits in such a way that is leading to a divergent structure. So it is something of a holographic pattern in the sense that you have a deflection caused by the Coulomb potential. We also had a look at the spider. So the spider is attributed to the interference between forward scatter trajectories, which are these two hyperbolic. And in fact, that's also what we found later on. And we also found things that people never predicted, namely the spirals. If you have this orbit that goes around the core and you combine with other orbits, you're going to get spiral-like structures. So what is going on? So they are really associated with interference carpets. So we decided to have a look at this because we think this was sometimes, not always, a case of mistaken identity, because in the past, people found that if you look at the direction perpendicular to the driving field polarization, when you look at these momentum maps, you see that every second ATI ring is missing. Can you see that? And the explanation that was obtained at the time was that this was associated to the interference between the long and the short direct ATI orbits. And this is actually a widespread belief. And it was, in fact, they found that exactly at the axis this would work. So this is also useful to look at these axes because here the Coulomb effects get canceled out. So you can use strong field approximation, you can use methods in which they are not important. Okay, but this is always the case. So we decided to have a look. And our conclusion was that this was a case of mistaken identity because if you consider orbit 3 and orbit 4, and you look at the spiral-like structures, they give you something in the axis. This is not symmetrized, I'll come back to this point, but you can see that here, orbit 4 gives you rescattering ridge, so it's what I said is pretty much like a rescattered orbit. Orbit 3 gives you this caustic here, and you combine both and you have these kind of fringes. So they may also lead to the carpet, and they're useful for ultrafast holography as these orbits are strongly interacting with the core. So this is a case of mistaken identity for us, and because people always thought it was direct, they never thought about the possibility of using this for holography. But in fact, in this energy range, they are very much interacting with the core. So they could be used for holography. And here are the features that we have found. So this is an experiment which was carried in Wuhan. To see this more easily, because the ATI rings are a problem, sometimes when you want to see things, we plotted this, we made some energy angle plots instead of going for a momentum map in the conventional way. And what you can see here is that here you do have this feature, and we consider here interference of orbits 1, 2, 3, and 4 using the QCSFA. And this is their experiment. Now, this is useful for holography. You see this separation, and in this region, the spider is suppressed, which is important because sometimes you want to see things and the spider fringes, they are very, very, very much present, and you miss a lot of information. But perpendicular to the field, the spider is suppressed. So we said, okay, but how can we rule out that this doesn't happen because of other orbits? Well, what was key for us was the region of interest, because if you look, this energy region is much higher than what you would expect for the direct ATI cutoff. And we decided to plot the SFA and look at what was happening not only at the axis, but in the vicinity. And we saw that in the vicinity, you would get a totally different behavior. We looked at, here is what you have with orbits 3 and 4, which are strongly interacting with the core. And here is what you would have if you consider rescattered ATI, here SFA direct ATI, and here CQSFA orbits 1 and 2. And the best agreement was really this one. So first, the energy was too high. It was far above the ATI cutoff, direct ATI cutoff. And you had the angular dependence that was very different. But the point I wanted to make as well here for you who are watching is that there are many carpets. If you have a field which has a half cycle symmetry, say if you have AT plus minus AT plus half a cycle, and the same for E, whereby A is the vector potential and E is the field, you are going to get this gap in 2 omega, so every second ATI peak is going to be missing. And this is something that holds if your field is sufficiently large that it can be approximated by a monochromatic wave. This comes from the field. This doesn't come necessarily from a specific type of orbit. So we have carpets in all these cases, but you need to establish if you have a Persian carpet, a Kelian, or if you have some carpet that maybe is coming from the Far East. So they're different. And this was interesting because it made us realize that there are many, many, many holographic patterns that are overlooked because of the very fact that people don't include the Coulomb potential and they cannot dissect these different pathways or separate. For instance, these orbits, these A and B patterns, here we consider that we have phase differences between start times smaller and larger than half a cycle. You have the Coulomb potential, you have the spirals, you have also these other, you have other things, you have other patterns, And it's difficult for us to compare with existing models because first, our tunnel axis is not fixed. It's going to depend pretty much instantaneously on what you have. Tunnel exits when it goes, the electron leaves and goes to the continuum. We have the Coulomb potential, so there is a big blurring between what is direct and what is rescattered. And there's no one-to-one mapping between Coulomb free and Coulomb distorted orbits, which is an important point actually that these people make, Shvetsov, Shklovsky, and Line some time ago. And it's important to know where you define your unit cell, because obviously to get the right asymptotic momentum, you have to propagate over many cycles, but you can only use a specific range of ionization events. For instance, when I was talking about type A interference, we're considering just events which were limited within half a cycle. Here we consider events which are still intra-cycle, but they are bigger than half a cycle. Here for this dash, we shifted the event in half a cycle. So these phase differences, they come all from different events, and the Coulomb potential is adding complexity to the whole situation. So we have different types of interference, and we are going to have some arbitrariness, which can pose a difficulty if you're looking at these things experimentally due to the unit cells. But we also ask ourselves, how about the prefactor? What is happening if you consider polarized system? And this was done very recently. And we consider that you don't have the ground state, that you have excited helium under the influence of a very strong middle IR field. And we place the initial state parallel and perpendicular to the laser field polarization. And we wanted to know what the SFA leaves out, because it can neglect bound state excitation, electron exchange, and the residual binding potential. Also, the SFA is a Born type approach because you construct that Born series I was talking about. So there is a very clear distinction between direct and rescattered electrons. And because you neglect the Coulomb potential, rescattering is happening along the polarization axis or very close to the polarization axis. This is if you have a linearly polarized field, which is what we were considering here. What you expect is that this signal coming from this perpendicularly polarized case would be very, 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 very suppressed by ionization, because you're living here close to another plane, and because of rescattering, unless you change this angle enormously, unless you manage to probe this. So we can have a look, and that's what we decided to do. I'm just going to show some example because it was really our work in which we tested many, many, many methods. But if you're curious, do have a look at our preprint, just out. So this is what you have for polarized helium. If you put your initial state parallel and perpendicular to the laser field polarization. Here you can see this ring here is the direct ATI cutoff. You can see very clearly the rescattering reach. And what you see, this is a comparison, this is done with Q-prop, one electron Schrodinger solver. You see that the reach starts to get suppressed. Can you see this is the rescattering reach? But you still have some part of the reach. And you also have the spider here. So you have some spilling outside the true UP cutoff. This, you have a lot of depletion, a lot of things going on. So it's not one-to-one correspondence. So we decided to look at QCSFA for the ionization potential. That would be the right one. And we were quite surprised. It doesn't agree that well, but you find also the reach. You find a reach both for parallel and perpendicular case, and you find all these structures. And I'm going to come to this point. Why is this overestimating? Because we also computed a spectrum, and here you would have a plateau. Why is this overestimating the rescattered region? If you now increase artificially the ionization potential a little bit, what you see is that you get some similarity with Q-prop. you have remnants of the ridge, you still have some spilling, but you don't have this ridge in the perpendicular configuration, so you expect rescattering to be suppressed. But here you have evidence that rescattering is not always suppressed, although you placed your target initially in a perpendicular configuration with regard to the field. So just reminder, Q-prop is influenced by a lot of other things like AC Stark shifts, different ionization channels such as read-back states, over the barrier ionization, depletion. So there are many other things that one needs to take into consideration, but still we think this is an interesting effect and we decided to have a close. So how to explain this? So if you look, let's look at orbit 4. We say orbit 4 is responsible for rescattering. Let's see what happens. So for this correct ionization potential from this excited state, what you see is that you have a prominent rescattering ridge in both cases, whereas if you decrease it a little bit, you see that is strongly suppressed. And what really happens is where your tunnel exit is. Where does the electron go to the continuum? If the electron goes to the continuum in a region in which the potential dominates, it's going to make a loop because you have a central force dominating. And the rescattering and all this effect is going to be much less directional. So if you can probe here, this perpendicular feature when you ionize, and when you rescatter, you have this whole range. Whereas if you have a tunnel exit that is large, the field is going to dominate and is going to give you what we expect, that you're going to have a rescattering that is directional. We did other studies, I'm not going to show. We looked also at angle integrated spectra using other methods, but pretty much the message is that maybe, depending on what you take into consideration or where you are, you don't always need elliptically polarized light to probe something that is perpendicular to the field, depending on the central potential that you are dealing with. So, okay, now how about applications? Because I was saying, okay, there's imaging, there is this and there is that. We want to know, if we are talking about phases, what can we apply to? I mean, one possibility, and this is something that we developed in collaboration with experimentalists in Frankfurt, is to look at parity of orbitals. And the key idea is that we want to see what is happening depending on the phases that are accumulated. First, in the initial bound state, because you're going to have that prefactor and you're going to have some influence depending on whether your state where the electron is initially bound is even, is odd, etc. And the phases that they're going to pick up in the continuum. And just to remind you, we have the fan, which is interference between orbits 1 and 2. They are leaving, one is leaving from this side, 2 is leaving from that other side. You're going to have 2 and 3, the spider, and you're going to have 3 and 4, which is the carpet, at least in the high energy region. So here you can see a schematic representation. Okay, so let's have a look. What we did is, because we wanted to minimize the effect of the continuum propagation, we have seen already from our previous figures that this is important, and depending even on the ionization potential, this can go crazy and be completely different and give you totally different effects. We needed atoms and molecules with similar ionization potentials and different parities. So we wanted to have a situation in which the continuum phases were similar, but the bound state phases were different. And depending on where it starts and where it finishes, one can show that you are going to have additional phase shifts or you're not going to. For instance, if you have even parity and you consider the fan, if they leave from opposite side, here in the even parity you have no shift, but in the odd parity you have a pi shift in the interference patterns. In the spider, they are leaving from the same side, so you're not going to have any type of shift because they pretty much pick up the same phase when they leave, and they're leaving from the same side with equal parity. And for the carpet, you expect a phase shift if your initial state is odd. So summarizing, orbits which interfere and are leaving from opposite sides are going to contain some phase shifts, a pi phase shift, and from the same side, no shift. And we're going to use that. So here we picked up argon and N2. And this is to ensure that the phase differences in the continuum, neglecting whatever you get from the bound state, are pretty much negligible. And that's why we picked up the same ionization potential. You can see here in this plot. And then what happened is you have something that is coming really from the bound state. So here we're going to focus in the carpet because it was the easiest situation with the resolution that we had. And here we have the spider where you expect some shift. We're going to see later on that actually this is the case. And the fan, no, spider has no shift and the fan has a shift. So we're going to use the carpet. This is the measurement. This is the results that we got with the TTSE. And this is what we obtained with the QCSFA. You can see very clear carpets in all cases. Here, you have to take other pathways into consideration, maybe bound states, maybe other things. So we went for the cleanest situation where we knew, okay, we have orbit 3 and 4 interfering. So let's have a look. And to see clearly, we normalize the spectra. So here you can see the differential spectra, which is plotted, and when you have pretty much even order, you have maxima for argon, minima for N2, and for odd, you have the other way around when you look at what is missing and what is still staying. You know, remember, every second ATI ring should disappear because of the interference between these spirals. Okay, so we could see that they were behaving as you expect, that you would have the phase shift, which you can then associate with the parity of the initial orbital from which the electron was leaving. Now, I mentioned multipath interference, and this is interesting because every time people were talking about photoelectron holography, they always focused on 2 orbits, either orbit type 1 or orbit type 3, or 1 and 2, or 3 and 4. So basically, always since the inception, even before we had this classification, you were considering, or we in our community were always considering the interference between 2 types of orbits. But could we have more than 2? And could we use more than 2 types of orbits to retrieve patterns that are associated with this? For instance, a modulation in the spider, which is what we're going to use. For that, we need to be able to look inside a laser cycle. So really, we have to resolve intra-cycle interference in a very, very, very fine way. And a big obstacle are the ATI rings, because they are very prominent, and once you have more than one cycle, they're going to appear. So they're going to obfuscate a lot of things, hence many cases of mistaken identity, of patterns that people see and we saw as well. And you have also, remember that we have these arbitrary unit cells, and they lead to some arbitrariness in the patterns in theory, and some asymmetry, because what happens is that you propagate for, but you are going to have arbitrary start and end points in time. So pretty much it is as if you would put an offset phase here in your vector potential and in all the fields that you're using in your computation. And depending on where you start, you can start, for instance, from a minimum and include the events which you have here within a cycle, or you can start a little bit later or a bit earlier and include only these events, or you could start from a maximum, etc., etc. And I mean, how do you decide? All these things are valid. You, at some point, you have to call the shots. You have to say, okay, if I include all the events within, say, 4 cycles are going to have ATI rings, you need to look at intra-cycle interference, so you need to reduce this, but you're going to have this offset, which is going to lead to some trouble. And here is just to give you an idea. For instance, these are the patterns that you obtain by using those offset phases. They look different. You see that the fan is distorted, the spiral goes to one side, goes to the other side, you know. One thing that we have done is to look at unit cell averaging. So we summed several unit cells and took an average, but this was an incoherent average to avoid the problem of having these ATI rings that would be prominent. So why not sum everything incoherently? And experimentally, what was happening is that these ATI rings and these high frequency structures, they can be filtered. So this is what you get. You see, these are symmetric, and in principle, you contain this map contains this momentum map, all information from several possibilities of unit cells, and that's what you would have in reality if you would look at intra-cycle interference and could remove the ATI rings, and that's what actually we have done. So here again, you can see the difference. This was unit cell just considering 0, and here is when you take the average. This is the filtered experiment, so you can see the spider, you can see the fan, and you can see you have some kind of modulations. Because we have a lot of high frequency structures also when they are not ATI rings. These are structures that come from the spirals, which you are superimposing incoherently. To be able to compare with the experiment, we had to filter the QCSFA, or they filtered it for us so that we could make the same comparison. And this is quite a fine result. Here you can see you have this modulation, which comes from other types of orbits in the spider. So the spider is always an obstacle if you want to look at other things as well, other types of patterns. And one way to overcome this, instead of going always perpendicular to the field, is to embrace the spider, but to look at something finer on the spider, which will come from other types of orbits, which, for instance, are causing the fan, or which are causing other types of interference. So let's have a look. We can also use for parity, right? Because we know that this modulation in the spider legs is caused by other orbits. So in fact, by the interference of orbit 1 and 2 and orbit 1 and 3. So we considered a 3p bound state in argon, and we expect, as we have seen before from this work with Frankfurt, that we're going to have phase shifts between orbit 1 and 2 and orbit 1 and 3. But here we're not using any reference atom to infer this. We are considering that we're going to have this modulation, so we can pretty much use one pattern on top of the other, or modulations on one pattern that come from the other type of interference. And if you include the prefactor or if you leave it out, if you include the prefactor, you see here, along these axes and close to the axis, you have a pi shift as you expect. And the carpet, as we also expect, also gives you a pi shift. So both axes, perpendicular to the field and along the field. And when you put the bound state and you look at the experiment, you also get a better agreement. This is these cuts here. So in fact, this is this one, this dotted one, which we're plotting second spider leg. And you see the maximum more or less where you expect. And they agree if you consider these phase shifts which come from your prefactor. Now, you also have to be careful because we are considering here in experiment a 3D situation, whereas in our method, we did a computation in 2D. So we need to include Maslov phases. For details, please see this paper here. It's very nice where they discuss. And this needs to be included every time the perpendicular momentum component is changing along the orbits. So we need to consider this in orbit 3 and 4. And if you include this correction, it also improves. So what you're going to have is you're going to have thicker fringes along the polarization axis, and you're going to have a steeper gradient along the spider legs. You can see here the red and the green lines, and that the agreement improves. We went like this way. Okay, yellow line, green line, and red line. So this is nice because you can actually see that you can probe these kinds of things using multipath interference, and you can overcome the difficulties that are many times caused by the spider. So I would like to conclude. I talked a lot about many things, but the message from this talk is really simple, and it is that the residual binding potentials are important when you are assessing holographic structures. And they bring so much richness to the whole situation, and the quantum phase differences that you need to take into consideration, they are also influenced by that. So at the end of the day, it's all about phases. So I'll use the opportunity also to advertise our review article on photoelectron holography, which was a lot of work to do, but makes this point. In fact, that's why we called it It's All About Phases, because it is, believe me. And I would like to thank my group. Some of these people are working on something else, but especially Andrea Maxwell, who played a big role in these computations. Arbitrary, who was doing this polarized helium work. Ex-students, Ahmed Al-Jawari and Tony Das, all the experimental groups that have been working with us on this. Eloise is working on something else. Cornelia and Gonhong are looking at tailored fields. So really, and our sponsors, of course. And do not miss, we're talking about seminars, so do not miss the Atto Fridays. Registration is as well free. I'm organizing at UCL, and two of my people as well, Cornelia Hoffman and Abi Bray. So do not miss the Atto Fridays. We have had a lot of speakers, and do have a look at our program. And thank you very much for your attention.
Thank you very much, Carla, for the wonderful talk and the interesting talk about electron holography and the role of the potential, the important role of the potential in our understanding of these features. So I don't see for now questions in the box, so maybe I can break the ice and start with one or two questions. And the first one is, yeah, maybe is a bit naive. And photoelectron holography really attracted a lot of interest in the last years, not only for the for how rich the structures are and for what we can learn about the laser dynamics, but also, of course, the aim is try to say something about the target. And you were showing now that actually from the holographic features it's possible to get information about the parity of the bound orbitals. That is important. And I would like to know if there is any possibility to have any information about the molecular structure.
In principle, yes. You just need to be able to assess how the structure is going to change. You need to, for instance, if you have a change, if you have a resonance, if you have something, this is going to manifest itself differently. And you need to be able to incorporate this in the theory, and you need to be able to track this. Because as you could see, everything is going to influence. The time the electron is in the continuum, where it left, how it left, the geometry of your state. If there's some rearrangement, this is going to make a huge difference. So in principle, yes, it's difficult maybe to model and maybe to infer, but yes, because every little thing that is going to change is going to lead to a phase shift, or is going to lead to another modulation in your patterns.
Yeah, and well, I remember also from the literature, the papers published by the group of Morishita, that they were suggesting that in the near forward scattered electron holography, one could try to retrieve any information about the molecular structure. And in the past, what we tried to do with our collaborator, really doing other type of theory, doing really TD-DFT, ab initio and black box calculations, they were trying to simulate this in a diatomic, change the bond lengths, but actually in the holographic feature, we were not able really to see an appreciable change of the holographic feature. So my question is, can you envision a way of going into this direction?
I mean, what I would try to do is see what type of interference is changing when you change the bond length. If they're leaving from the same side, probably you're not going to have a lot of change. If they're leaving from different sides, it's very likely that you will. If the tunnel exit is altered, you also are going to have something. The difficulty is, if you do a black box computation, it's a blessing and a curse. It's a blessing because it's very flexible. For instance, we're trying to do this stuff for tailored fields, and we are struggling with all sorts of things that you cannot imagine. Because our model has a huge predictive power, but is not flexible in the sense that you are solving a boundary problem in the complex plane. Okay? So it's nasty, and you need to overcome this nastiness, but once you have done it, you can switch things on and off. If you have a computation that is black box computation, as you say, the difficulty that you're going to have is that you have everything there. So you're going to have ATI rings, you're going to have structures which are hugely prominent, and you may be willing to identify an effect which is subtle. Because unless you have a huge resonance or something like that, the effect that you're trying to look at is subtle. Okay? So you need to know where you get this thing from. And to be able to know, you need to identify, okay, what orbit is interfering with what orbit, and what is this leading to? Okay? And it's not trivial, but it's feasible if you have enough predictive power, because you know what to look for.
Yeah, sure. Good. Thank you for the answer. And well, I don't see questions for. I don't see any questions in the box. Then I have time to ask maybe another question.
Yes, go ahead. And I don't know what is happening with people that they are shy today.
So I encourage people, please participate to the discussion. It's a super interesting topic, so don't be shy. Write your. I see. Sorry, I see one question now from Dejan. So the question is, for excited helium, how you create parallel and perpendicular states? In experiment, you measure average sum over M.
No, what we do is we just fix it. So we consider that is perpendicular, and we don't consider any. We consider the average. We use games, but we don't look specifically at what is happening to the momenta or to the angular momentum case.
Okay.
We just fix it.
Okay, clear. And I don't see other questions now. Please, again, I encourage the audience to ask. Maybe we can use 1 minute more. And in the meantime, I can maybe ask the question that I had in mind. So an important point that you made, that it's important to consider the residual potential to have a realistic interpretation of the electron trajectories. And in this framework, direct trajectories and rescattering trajectories are, I mean, the concept itself of direct and rescattered electrons becomes a bit more blurred. And this is important not only for holography, but also for laser-induced electron diffraction, right? Because for example, if you want to exploit the time resolution of lead, you need to lock the time of ionization and time of rescattering. And do you think that including the potential and having the electron, let's say, dancing around your target could have an important influence of our interpretation of time-resolved laser-induced electron diffraction?
Could have, but from what I know, correct me if I'm wrong, when you look at lead, you go exactly to these high energy electrons, right?
Ideally, but since the signal is low, you go to 5 or 6 UP electrons, where I think you could have a strong contribution. Right?
You could have. You could have, because it's a borderline case. I mean, I know people try to go as much as they can to high energy electrons, because then you know whatever you have from the rescattered scenario dictated by the SFA is going to be more or less okay. It's going to be accurate. But the problem is really this intermediate scenario. So if you cannot restrict, if your signal is too low, you could have some influence of things that, strictly speaking, wouldn't be rescattered and wouldn't be direct, would be something in between.
Yeah, good.
Yes. And this division is actually quite artificial. It's interesting because you yourself think in these terms, and you talk to people who have used SFA forever, including yourself, and you think in this term, what is direct, what is rescattered, but it's something that is artificial because this was imposed by the way that SFA is constructed, which is when you have a Born type approach where it's clear cut, because you have a field free Coulomb free continuum or potential free continuum, and you have that very specific interaction there that you put in your series, whereas reality is different.
Yeah.
So it's just not trivial to understand what is going on.
Good.
Yeah, and even, for instance, this the fan, which was the first case we looked at, this, I mean, if you think about it, people would say, this double slits that you get just combining the direct 1 and orbits 1 and 2 from the strong field approximation. The fan is a distortion of that. So you could still say maybe orbit 2 is direct, but it is really direct because it's being distorted by the potential, and you're having a distortion that is unequal depending on the angle you're considering for your scattering or for your final momentum, right? So it's being deflected, but it's not like a hard scattering that you would have for the type 4 orbits that we have discussed here.
Sure.
So I think we try to avoid this because it's a difficult problem, but at some point we're not going to have any choice but to embrace it. you know, because everything you do in lead, you say, okay, you try to make your momentum as high as possible. In looking at the carpets, you look at the perpendicular case, you know, because you want to minimize the influence of the potential, but eventually it does play a role. So either you minimize it or we find a way to deal with it, which is more difficult.
Good. Yeah. Unfortunately, our time is over, and thank you very much, Carla, for this answer and in general for your seminar. Thank you for reminding us about the Atto Fridays, and I also remind to the audience that on next Wednesday we will have the next, on the 21st of July, we'll have the next AttoChem webinar. And with this, I thank you, Carla, again, and all the audience, and thank you. Bye-bye.
Thank you. Thank you, everybody. Stay safe and have a good afternoon. Bye.
Bye.